Good day, everyone. Welcome to the AOML NOAA Science Seminar. This is presented by the Hurricane Research Division. Today we will feature Dr. Sarah Ditchek, and she will be speaking about the recent work on the impact of dropsondes on tropical cyclone forecast. If you have questions, please put them in the chat as we will go through the seminar. Thank you. Go ahead, Sarah.
Thanks, Shirley. So today, as Shirley mentioned, I'm going to be discussing some recent work on the impact of dropsondes on TC forecast. And this work was funded by the fiscal year 18 Hurricane Supplemental, and it ended up being split across 4 different projects. Today, I'm going to be talking about 3 of those projects. They're the projects at the top of this slide in the presentation guide, the consistency metric, the overall dropsonde impact, and the relative dropsonde impact. If you want to hear about the 4th project, you have to wait till the tropical conference. Check out Jason Sippel's talk there. So I'm going to start off with some very broad motivation on why we would want to quantify the impact of dropsondes. So the overall goal of assimilating OBS into models is to try to make the model's initial state as close to reality as possible to hopefully achieve more accurate forecasts. Now, this image summarizes the global observing system. Data collected from these generalized categories are assimilated into global models like the GFS and also regional models like HWRF and now HAVS. Now, when we're talking about DA for TCs, it's not only important to have these conventional and satellite OBS in this figure. For TCs, in situ OBS of position, intensity, and structure are obviously key. And to do that, TC recon missions are conducted using aircraft like NOAA's P3 and G4, shown here in this image. And these aircraft fly into storms collecting in situ data to improve TC forecasts. Now, over the past several decades, there have been numerous peer-reviewed studies that quantify the impact of recon on TC forecasts. And these types of studies are needed because if we simply add additional data to forecast models, even if it's high-quality data, it doesn't ensure improved forecasts. Now, perhaps the most valuable for understanding the impact of recon are those studies that use large multi-year samples, because these are less subject to inherent variability among TCs or even years. Yet there have only been a handful of these large sample studies of the impact of TC recon on TC forecasts. And there's around 5 of them, actually. These studies varied in the type of recon they assessed. They looked at individual types of recon and overall, but they did all find that in general, recon typically benefited TC forecasts. And these benefits increased with more advanced DA systems and more advanced modeling systems. But despite the documented benefits of the recon, these studies left some important questions unanswered. So, for example, only 2 of them assessed how recon impacts varied by TC intensity. Only 1 of them compared the impact of recon during sampled periods to the impact of recon during unsampled periods. And none of them looked at the impact of recon on PMIN or significant wind radii forecast. And they also used either global models or older versions of HWRF. So these shortcomings make the systematic assessment of recon's impact difficult. Now, from this suite of currently operationally available recon, it's particularly useful and important to understand the impact of dropsondes on TC forecast. And why is that? So as most of us know here on this call, dropsondes are these single-use instruments that are launched out of the aircraft to record data like pressure, temperature, humidity, wind speed as they fall to the Earth's surface. And they're really valuable since they enable data collections in regions where it's too dangerous to fly, like the turbulent regions near the surface, and in regions that aren't able to be seen by satellites, like within clouds and at the surface. But as we know, dropsondes are expendable and costly. They're around $900 each. And since at least 20 to 30 dropsondes are launched per flight, they add considerably to the cost of a typical airborne mission. Now, this added cost could be justified if dropsondes improve TC forecasts and subsequent warnings and help reduce evacuation footprints, economic impact, and loss of life. So therefore, there have been numerous studies that assess the overall impact of dropsondes on TC forecasts. Yet again, while there have been numerous studies, large sample sizes have rarely been used. And again, this makes the systematic assessment of their impact difficult because of the year-to-year, TC to TC, forecast-to-forecast variability. So to demonstrate this, I have this figure. This figure both summarizes that overall impact of dropsondes from previous studies. Track is on the left, maximum sustained 10-meter wind speed, or Vmax, is on the right, but it also highlights that sample size drawback. So briefly, the x-axis is your forecast lead time. The y-axis is the impact of having dropsondes measured by % improvement or degradation. All the different colored lines are the different studies, and they're colored by their sample size at forecast hour 0. So there's a lot of lines on here, but I want you to really focus on those thick yellow lines. Those indicate those studies that had a sample size of 100 or more at 0 hours. And I'm using 100 as a benchmark for a large sample here, but often even if you have 100 at 0 hours, at long lead times, the sample size ends up being quite small because not all forecasts go out 5 days. There have only been 3 large sample track impact assessments and 2 large sample VMAX impact assessments. And as I mentioned on the previous slide, there have been no large sample PMIN or significant wind radii assessments. And this is particularly important in mission because we know that pressure and size of a TC correlates strongly with its damage potential and is important for TC hazards forecasts and warnings. So that brings us to this talk. The recent work we performed addresses the shortcomings found in the literature for both recon and dropsonde data impact studies. The work assesses the impact of dropsondes on TC track, intensity, and significant wind radii over a 4-year period. It does so by verifying model forecasts against the National Hurricane Center best track following NHC verification rules. And to accomplish this component, it was most efficient for me to create a software verification package. I'm a huge Disney fan, so I got it to have a Disney acronym, GROOT, graphics for OCs and OSCs, and other modeling applications on TCs. And this package ended up not only being useful for the work you'll see here today, but also it's been utilized by others for their research. And so if you're curious, the package is on GitHub, it's on my NOAA account page, and it's forked on the AOML GitHub page. So again, I'm going to be discussing 3 different papers today, all recently published in AMS's WAF. I'll then summarize their main takeaways, provide some recommendations for future progress, and detail some ongoing work related to TC recon impact studies. So the first paper, it details a new metric to identify forecast consistency. And this metric was incredibly vital to our analysis in all subsequent papers, since as you'll soon see, if we rely solely on commonly used verification metrics, it could lead to a misinterpretation of results due to skewness caused by outliers. Now, the next paper used this consistency metric to analyze the overall impact of dropsondes. And then the third paper details the relative impact of dropsondes in different regions of a TC on TC forecasts. And results in 2 and 3 represent the most comprehensive assessment to date of the overall and relative impact of dropsondes and any airborne observing system on TC forecasts. So the first paper, first up is that new metric we use to identify consistency. So this consistency metric was created when analyzing results from our work on the overall impact of dropsondes on TC forecasts. And so what I'm going to do on this slide is show you an example where using commonly used verification metrics would have led to a misinterpretation of results, thus motivating the need for this consistency metric. The example I'm going to show you is for the direct impact of dropsondes on VMAX forecasts. And by that, I mean these graphics are only going to include those individual forecasts from Atlantic Basin TCs with dropsondes in DO2. And results come from my 4-year sample that I mentioned earlier that I'll detail a lot more in the next section. So first of all, I keep mentioning commonly used metrics. What do I mean? So that's the mean absolute error, the MAE, and the MAE skill. They're sometimes used together, often only one or the other is used. For those who don't know, the MAE, it represents a group of forecasts that have been averaged together. The MAE skill represents the improvement or degradation of one group of forecasts compared to the other group of forecasts, which is considered the baseline. So here what you're seeing is the MAE on top and MAE skill on the bottom. The x-axis is your forecast lead time. Beneath that is the sample size. You could see the sample size is quite large. At 0 hours, we're at 375, and we're over 100 at 120 hours. The green line is my all experiment that allowed dropsondes. It's essentially out-of-the-box basin scale HWRF. The red line is my no experiment that denied dropsondes. Otherwise, there are no differences between these experiments, so any of the differences you see here is solely due to the assimilation of dropsondes. So overall, despite some variability present, there is 4.4% improvement on average, with improvement at long lead times reaching up to 10%. So this might lead one to say that overall, dropsondes improved VMAX forecast, particularly at long lead times across our 4-year sample. But I'm going to use 108 hours here as a representative example for this graphic. And as you could see, there was around 5% improvement at 108 hours. But now let's take a look at some other metrics. First is a frequency of superior performance, or FSP, which indicates how often one experiment outperforms another experiment. And now you also have here the median absolute error, which we're calling MDAE, and the associated MDAE skill. I'm now highlighting that same forecast hour, 108 hours. And as you could see, the all experiment only outperforms the no experiment 43% of the time, and the median was -5%. So what this means is the error distribution was non-normal. Here it was positively skewed, and that led to this inflated MAE skill at 108 hours. But this didn't just happen at 108 hours. This happened at multiple lead times. And so when digging into these results further, what we found was that TCs from 2019, 1 out of the 4 years, and particularly one TC, Dorian, was actually driving all the improvement found in the MAE skill. So instead of saying that dropsondes led to overall VMAX improvement at long lead times of up to 10% over our 4-year sample of 2017 to 2020, we actually have to be a lot more nuanced. The Dropsondes led to Vmax improvement for TCs in 2019, particularly Dorian. And this obviously is a huge difference than saying that there's overall improvements across the entire sample. So we needed a way to combine useful information from several important verification metrics to assess consistency in results. And the new way should ideally maintain simplicity users enjoy when evaluating the MAE and MAE skill, but it should also add context about the error distribution to help the user understand where more exploration might be needed. Also, if effectively done, the time required to assess results should remain nearly the same, but misleading conclusions can be avoided. So this new metric called the consistency metric is our solution to the problem. I'm sure there are other ways to do this, but this is what we found worked really well. Now, to create this consistency metric, we applied thresholds to 3 different metrics to create a suite of outcomes. And I'm going to use this outcome matrix to define the outcomes that together create the consistency metric. As you probably guessed, those 3 metrics are the MAE skill, the FSP, and the MDAE skill. So the first outcome we have is fully consistent. There is one way for an outcome of fully consistent improvement or degradation to be achieved. So I'm going to use fully consistent improvement as the example here. For the outcome of fully consistent improvement, static thresholds of greater than or equal to 1% were chosen for both the MAE and MDAE skill conditions. And these thresholds were chosen, though they might seem quite low, but testing revealed that the sign of the threshold is way more important than the amplitude to measure consistency. Higher thresholds like 2.5 or 5%, it just creates a more stringent metric. Now for the FSP conditions, a little more complex. There's a dynamic threshold that we actually adjust based on the sample size at that particular forecast lead time. And we abbreviated it DYN for dynamic. And FSP is a really natural place to include such a threshold because FSP depends on the frequency instead of the error magnitude like the MAE and MDAE skill do. So the DYN formula and curve is shown here. Your x-axis is your sample size. The y-axis is that threshold that you have to beat. And note how if you go from right to left, your sample size is decreasing. And as your sample size decreases, the threshold you have to beat gets higher. So what this does is it ensures 2 things. First of all, it ensures that a fully consistent outcome can't be achieved for small sample studies with large errors and skewed distributions. But also it ensures that if you have a small sample study with a non-skewed distribution, you can't really generalize it to apply to all cases unless it passes a really stringent threshold. So if all 3 of these thresholds are met, then that particular lead time is identified as having fully consistent improvement. Similar conditions apply to the outcome of fully consistent degradation. But forecast hours can vary from one lead time to the next. And so we didn't want to just have a fully consistent outcome and a not consistent outcome. Because maybe, let's say there's a case where 2 of the thresholds passed, but 1 just barely missed. And so to add more nuance, what we did is we added the outcome of marginally consistent improvement. And there are 3 ways for a forecast to be designated as marginally consistent. I'm going to use option 2 as an example here. So let's say that the MAE skill and the FSP both passed their fully consistent thresholds, but the MDAE skill just missed. Then as long as the MDAE skill didn't deviate too far from the MAE skill and FSP, then it's identified as having marginal consistency. But if the MDAE did deviate too far, then that forecast lead time is identified as having no consistency, signaling that the distribution is actually skewed. I filled out the rest of the table for no pun intended for consistency's sake, but I know this is a lot here. All of it's in our paper. You don't have to thoroughly read through all the conditions. And on 2 slides, I'm going to be giving a practical example, which will make this a lot easier to understand. But before that example, I have a flow chart to make these steps a little bit more clear. So at each lead time, we go through this. So step 1 is, do results at this lead time match or exceed thresholds in either of the fully consistent outcomes? If yes, then fully consistent improvement or degradation is identified for that lead time. If not, we go to step 2. Do results at this lead time match the marginally consistent outcomes? If it does, then it's marginally consistent improvement or degradation. If it doesn't, then no consistency is found. As promised, I'm now going to give a practical example, and I'm going to be using the example I've already shown you through the lens of this consistency metric. The MAE skill, FSP, and MDAE skill that I went over earlier in the slides are given here. And I'm highlighting that forecast hour that I specifically talked about. And for demonstration purposes, what I'm going to be doing on this slide is just focusing on one outcome, the outcome of fully consistent improvement. And I'm going to be showing blue boxes at lead times where each individual metric passed their associated thresholds. Again, just for that one outcome of fully consistent improvement. So those boxes are now shown. And if we look at that 108-hour lead time, we see that only one of the 3 metrics had a blue box. And so one of the 3 metrics passed their threshold. So that means that this lead time had no consistency was found. And so even though there's this elevated MAE skill, again, no consistency was found. And as I explained earlier, that since the distribution at that lead time happened to be skewed. Again, this is just for one of the 5 outcomes. So we want to concisely relay information, not just for one outcome, but for all the outcomes. And the way I'm going to do that is assign colors to each of the outcomes and display them at each lead time on the MAE and MAE skill graphic. The shaded colors in that consistency table a few slides back are used. And so now, finally, is the MAE on the top, MAE skill on the bottom, with the associated consistency metric at each lead time. Now, if you recall, the MAE skill was found to be inflated at long lead times. And this information is now very clearly concise and concisely relayed on this one graphic. The outcome of fully consistent or marginally consistent improvement isn't found at those longer lead times where you have such elevated MAE skill. And so that's suggesting that the FSP or the MDAE must have differed from the MAE skill and the distribution is skewed. And so if you saw this result for your 4-year sample, it would then say, hey, that looks a little bit odd. Let me now dig in a little bit further and see why there's that inflated MAE skill. And that's then how it led us to find out that this improvement was driven by TCs from 2019, particularly Dorian. So to summarize, this consistency metric can be viewed as a tool to increase your confidence in the interpretation of results, but also identify, like I just explained, where additional analysis might be required for a particular metric and forecast lead time. But the great news is that it maintains the simplicity users enjoy when looking at the MAE and MAE skill. It's right there, it's clear, it's really fast to interpret and understand, but it helps us avoid making these conclusions that are misleading given skewed samples. And it could be used for any variable, any number of sample sizes, including tons of stratifications, which are really important to understand the distribution of the errors in your sample. So now that we have this consistency metric, what can we do with it? So we can create a consistency scorecard, and you can take consistency metric from multiple variables and compress them down into one graphic, which will enable this quick yet comprehensive initial assessment of the consistency of your results. So I'm going to use the consistency metric outcomes from the direct impact of dropsondes on TC track intensity and size forecasts as a representative example. And so these results I'm going to show you include individual forecasts from Atlantic Basin TCs with dropsondes in DO2. So this Vmax row here is, you've already seen, that's the example I've been giving throughout the presentation. The x-axis is still your forecast lead time. And now on the y-axis, you have different variables: track, Vmax, Pmin, and significant wind radii. I'm not going to go over the results here. I will talk about these results in the next section, but you can essentially see you're getting an accurate snapshot of what your results are, and then you can dive in deeper to each of these different variables as much as you'd like. A quick plug for those of you not familiar with the AOML Hurricane Model Viewer. It's a website that hosts all kinds of graphics for products, for experimental and operational NOAA models, and I really, really encourage you to check it out. Given the utility of this new metric, Gus Alaka suggested we find a way to add it to the website and to demonstrate its capability. And so what we did was add a new tab to the website dedicated to post-TC verification, and this filled a gap on the website since there wasn't a previous capability like this. So you can see the landing page here. The arrow points to the new tab. For the sake of time, I'm not going to be demoing the website. There is a QR code here to take you to the website, and then you could head on over to that tab. But some quick background on the capability: I generate graphics after any TC worldwide dissipates, and also for the entire season by basin. I usually get graphics up a day or two after it dissipates, and then I rerun the basin statistics quarterly, perhaps, unless there's a highly impactful storm and I'm asked to run it sooner. And I do want to give a quick shout out to the AOML Hurricane Model Viewer team who were involved with that tab going live, from helping with the aesthetics of the page to troubleshooting issues to making sure that the data I have to run my code is present and up to date. So thanks, guys. So let's summarize this section. I'm going to do that by sharing 3 main takeaways. The first is that I hope I've convinced you that the MAE and MAE skill can be misleading, even with a small sample size. We tested this with sample sizes 1,000 to 2,000, and it still can be misleading. And as I showed at the beginning of the talk, if the distribution of errors is non-normal, incorrect conclusions can be reached if only considering the MAE and MAE skill. And of course, this is particularly true for smaller samples, but as I just mentioned, it can happen up to a sample size of over 1,000. Now, the consistency metric compresses information about the error distribution in a straightforward way, and by identifying these disparities between the MAE and MAE skill and the distribution, which would signal that additional analysis might be needed if you want for that particular metric. So if we augment these MAE and MAE skill graphics at each lead time with a consistency metric, it does still maintain the simplicity of NHD-based verification methodology with the MAE and MAE skill, but it ensures a more accurate and holistic evaluation, not just of the impact of observing systems like Dropsondes, which I'm going to be talking about here, but also of new modeling systems and model upgrades on TC forecasts. So additional steps to ensure better understanding of the distribution could be analyzing individual metrics over the lifetime of an individual TC, and of course, doing numerous stratifications. And again, this metric was really needed to analyze results from our Dropsonde impact studies, and it's going to be used throughout this presentation. So next up is our paper that assessed the overall impact of Dropsondes on TC forecast. You can find it at the QR code on this slide. So this project marks the most comprehensive assessment of the overall impact of Dropsondes on TC forecasts of track intensity and size to date, and includes assessment of the impact of Dropsondes by year, by data availability, by initial intensity, by ongoing intensity change, and by choice of intercore error covariance. To do that, 2 model experiments were run, one that allowed Dropsondes and one that did not. And since no other differences were allowed, differences in model output highlight the impact of the Dropsondes. Experiments were run covering active North Atlantic Basin periods in the 2017 to 2020 hurricane seasons, and this resulted in 634 cycles, 2,139 individual forecasts covering 92 TCs, 41 of them had Dropsondes. Now, the reason why there were more forecasts than there were cycles was due to the choice of model for these experiments. This project used the basin scale HWRF, which was identical to the 2020 implementation of the operational HWRF, except in 2 key ways. And I'm going to use this map to demonstrate those differences. So this solid line is the parent domain of the operational HWRF. It relocates from one forecast to the next and is initially centered on one high-resolution movable nest. Now, this solid line is the parent domain of the basin scale HWRF. It's large and static and covers nearly all of the National Hurricane Center area of responsibility, now shown in black. And it also can have up to 5 high-resolution movable nests, now shown here, triggered by how many additional TCs are present in the basin. So while there were only 634 cycles in the experiments, each of those cycles can have up to 5 TCs. Now, in both HWRF and the basin scale HWRF, DAs performed on these high-resolution movable nests associated with each storm. That's DO2 and DO3. Okay, so I want to give a synopsis here. Over the 4-year period, there were over 106,000 individual temperature observations assimilated across those 41 TCs with Dropsondes. And yes, there are other observations from Dropsondes that were assimilated, like winds and humidity, but for accounting purposes, I just tallied up the temperature obs. So here what I've done is included a graphic of the TC relative plan view distribution of assimilated Dropsondes. There's an axisymmetric distribution within the inner 500 kilometers, and then outside of 500 kilometers, there's this northward preference of sampling the synoptic environment ahead of the TC passage, mainly by the G4. On the right is the radial view distribution of the assimilated Dropsonde, shown in plan view on the left, and there's a few areas I want to point out, and I'll be shading the corresponding areas on the left graphic. So first, we see this peak in the inner 75 kilometers. This represents the inner core drops that are dropped around the center and around the RMW. Between the first and second peak, there's this increase. These are the P3 minute endpoints and the G4 inner ring circ. This second peak represents the most frequent location of the C130 endpoints around 200 kilometers. And this final peak just outside the 300 kilometer radius represents the G4 outer ring circ Dropsondes. Okay, so preview of what's coming up for these results. The variables included again in this analysis are track intensity and significant wind radii. Forecasts are verified against the NHC best track following NHC forecast verification rules. Now, all the results you're going to see are homogeneous samples and are for Atlantic Basin TCs only. And again, for analysis, I'm using GROOT, which includes the consistency metric. So there are 4 main takeaways that I'm going to cover. First, direct sampling of TCs with Dropsondes yields the greatest forecast improvements, though improvement is heavily dependent on DA quality. Dropsondes benefited all intensity categories, though intensity-dependent impacts were present. DA deficiency still exists, particularly for TCs undergoing intensity change. And directly sampling the region of hurricane force winds improves our 64 forecasts. Now, naturally, I'm not going to show all the graphics to create these takeaways. I'm going to be showing results shown in the form of consistency metric scorecards, like the one I showed you a number of slides back. If you want more details than what I'll show today, check out our WAF paper. Okay, so now to the meat of this talk. The first takeaway, direct sampling of TCs with dropsondes yields the greatest forecast improvements. I'm going to pause there because I'm going to tackle that one first. So what you're seeing here are consistency metric scorecards. This takes the full sample in North Atlantic Basin TCs, stratifies it down by data availability into individual forecasts from North Atlantic Basin TCs with dropsondes on the left and without dropsondes on the right. Again, consistency metric scorecards, if the greens generally indicate improvement and the reds indicate degradation. Now, what you could see is that nearly all of the improvement is coming from the graphic on the left, which is the one where individual forecasts did assimilate dropsondes in DO2. On the right, there is some green, but there's also a lot more neutral and some smatterings of degradation in there as well. So here, it's direct sampling TCs with dropsondes are yielding the greatest forecast improvements. If we take this graphic on the left, we can now stratify it down by inner core covariance choice. And that's what you're seeing here. It's the direct impact of dropsondes stratified by covariance. These are individual forecasts from North Atlantic Basin TCs with dropsondes and DO2 that on the left did use H-Whorf cycled covariance, and on the right did not use H-Whorf cycled covariance. In other words, it used GDAS covariance or global covariance. And what you can see here is that nearly all the impacts are coming from those forecasts that did use H-Whorf cycled covariance on the left. And particularly notable is the impact of dropsonde data on TC significant wind radii forecasts, since naturally improving those forecasts leads to the more effective TC hazards forecasts. But you could see on the right, there is degradation, there's a lot of there's some marginally consistent improvement and a lot of neutral impacts. Takeaway number 2, dropsondes benefited all intensity categories, though intensity-dependent impacts were still present. You can see that here, this is the direct impact of dropsondes stratified by initial classification into tropical storms, category 1 to 2 hurricanes, and category 3 to 5 hurricanes. What you see here is that there is green in all of these different categories, which means that there's improvement found for all the categories. And what's really great about seeing this result is that it implies that the physics and DA improvements that have been made over the years really ameliorated that degradation that used to be seen when various types of recon were assimilated into hurricanes. So that's great news. What we also see is there's this different intensity-dependent impacts. We could see that there's a more immediate impact of the dropsondes for stronger TCs. Now, this result is qualitatively similar to results that were obtained from an earlier recon assessment that used a 2019 version of H-Whorf, and it was published in SWISLAC 2022. But it isn't clear whether these intensity-dependent impacts of recon is a general result or if it's just a result that's specific to H-Whorf. So what do I mean by that? So, for example, in Sipple et al. 2022, what we found was that if we added recon data to GFS, it more robustly improved forecasts of hurricanes at long lead times than tropical storms at long lead times. So that's different from what we're seeing here. So more work needs to be done to understand those impacts, intensity-dependent impacts. Takeaway 3 is that DA deficiencies do still exist, particularly for TCs undergoing intensity change. So here you see the direct impact stratified by ongoing intensity change into intensifying, steady state, and weakening TCs. So the most benefit of dropsondes occurs in steady state TCs. We see a lot of green. It's overall beneficial. There are some benefits to TC size for changing TCs, but there is also some degradation in track and intensity. And this suggests that there likely is still a DA deficiency. Maybe we need more frequent cycling or need 4D and VAR. Takeaway number 4 is that directly sampling the region of hurricane force winds improves forecasts of the 64-knot wind radii. You can see this here. This is the direct impact by year. This is stratified down by 2017 through 2020, which is the 4 years of our studies. The x-axis is still your forecast lead time. Something looks different, right? One thing doesn't look like it belongs. The 2017, what's going on? There is a lot of degradation in 2017 at short lead times. You don't see that in 2018 to 2020. So what we did was we stratified down the radial distribution of dropsondes into the various years, 2017 through 2020. And that's what you're seeing here. What you're also seeing on top of that is dark shading, what we're calling the R64 window. I looked at the mean plus and minus the standard deviation of the observed best track R64 values, and then tallied up how many assimilated observations, dropsonde observations occurred in that window. And what you could see is that in 2017, we had under 1,000. And then in 2018 to 2020, each year had about 3 times the amount. So we feel that the sparsely sampled R64 region in 2017 potentially was leading to this degradation found in 2017. Obviously, more work needs to be done to understand that. So to summarize this section, this project again marks the most comprehensive assessment of the overall impact of dropsondes on TC forecasts of track intensity and size to date. In this section, I presented supporting graphics for all these 4 main takeaways, but they're all kind of saying the same thing, that dropsondes are very valuable, extremely valuable for TC forecasts of track intensity and size, but it's heavily dependent on DA quality. Okay, paper number 3 here. This next paper expanded on the work of the previous section to examine the impact of removing dropsondes at different distances away from the TC center on TC forecasts. So in doing so, this project also marks the most comprehensive assessment of the relative impact of dropsondes on TC forecasts of track intensity and size to date. And I'm going to show you how we did this. So if you remember, I showed this graphic a number of slides ago. It's a number of assimilated dropsonde observations in our 4-year study by radius on the x-axis and number of assimilated ops on the y. And there are 2 particular lulls here, natural lulls in recon sampling, one at 75 kilometers and one at 250 kilometers. And what this does is it splits up our distribution quite nicely into 3 different sections, and we use these lulls to define our experiments. So it splits it up into the inner core region, the near core and outer vortex region, and the synoptic environment region. So what are these experiments that we created from this? Well, before I get to that, I want to remind you of the 2 experiments I just talked about, the overall dropsonde impact section. That's the all experiment on top here called all drop, and the no experiment on the bottom here called no drop. When you see gray shading, that means where dropsondes were allowed to be assimilated. White means they were not allowed to be assimilated. So using the lulls in recon sampling at 75 and 250 kilometers from the left-hand panel, we created 4 sensitivity experiments. That's seen here. The blue experiment denied dropsondes inside of 75 kilometers, and it's called the no inner core experiment. The purple experiment denied dropsondes inside of 250 kilometers, and it's called the no vortex experiment. And then we have their opposites, essentially. The orange experiments only allow dropsondes within the inner 75, and it's called inner core only. And the gold experiment only allowed dropsondes inside of 250, and it's called the no environment experiment. So we wanted to and needed to create a new methodology to compare the relative impact of these sensitivity experiments to a common baseline. In other words, how better are these or not better, how better or worse are these sensitivity experiments compared to perhaps the experiment that allowed dropsondes and didn't deny any dropsondes? So what you're seeing here is a consistency metric scorecard for 5 of the different experiments shown on the previous slide. Each of these experiments were compared to the same baseline, that experiment without dropsondes. So all drop is in the top row, and the sensitivity experiments are in the bottom 4 rows. Now, the x-axis goes here only from 6 to 60 hours, and so I wanted to point that out. If we were to make an educated guess about which sensitivity experiments maybe, let's say, perform much better or even much worse, but let's say much better than all drop, maybe we would say the purple experiment. There looks like there's 6 dark green squares compared to 3 in the all experiment, which is the green experiment. But what about the others? We needed a way to objectively identify this relative impact of these sensitivity experiments to all drop. And so what we can do is we can actually assign each of these different outcomes a value, as you see here, and let me drop those in here, and we could create what's called an overall consistency score. For a lot more details on that, check out the first paper I talked about, the consistency metric paper. What we can do now is we can average each of these rows together, each of these rows independently, and then multiply by 100. And this gives us a sense of the overall consistency of each of the experiments. So if a total score of 100 would mean that every single lead time had fully consistent improvement. If we had a score of negative 100, that would mean that every single lead time had fully consistent degradation. So based on the value you get in now column B, you can kind of see where you are on the scale, closer to all fully consistent or all full improvement or all fully consistent degradation. So now that relative impact part. If we take the difference between each of the sensitivity experiments and the same baseline, here the all drop experiment, we now have column C. And what we did is we devised this relative impact category table, which allows us to identify very quickly which of the experiments had either large or moderate improvement or degradation relative to that baseline here, all drop. So when we look at this graphic now, if we look at A, remember that thought experiment where I said, oh, maybe the purple experiment outperformed the green experiment, but we don't really know for sure. How do we quantify that? If you look at column C, you could see that only one of the sensitivity experiments popped out at us, and that happens to be the purple experiment as having moderate improvement compared to the all drop experiment. Okay, so now that I went over that methodology, let's get into the results from this paper. So a preview of what's ahead. Again, we're looking at track intensity and significant wind radii. Forecasts are verified again against NHC best track following NHC forecast verification rules. These are homogeneous samples and only for Atlantic Basin TCs. Different from the last section, though, given the results of the previous section that dropsonde impact was really only realized when using H-dwarf cycled covariance, for this paper, we focused on a subset of our full sample. We focused on just those forecasts that had dropsondes and used H-dwarf cycled covariance. And still, because we had a 4-year sample, the sample size was still quite large. And again, for analysis, I'm using GROOT, and that includes the consistency metric. So there are 4 takeaways for this section as well. The first is that removing dropsondes anywhere, particularly from the vortex, substantially degraded Vmax forecasts. The second is that in-vortex dropsondes contribute to a majority of the overall impacts of the dropsonde observing system. Third, track forecasts of weak TCs benefited more from environmental sampling, while track forecasts of strong TCs benefited more from in-vortex sampling. And finally, inner core only sampling strategy should be avoided, supporting a change made to the U.S. Air Force Reserve sampling strategy in 2018. The results are going to be shown in the form of relative impact scorecards, which I'll explain on the next few slides. There's going to be one result from takeaway number 4, that's going to be using the consistency metric. Okay, so the first takeaway, removing dropsondes anywhere, particularly from the vortex, substantially degraded Vmax forecasts. So this is a relative impact scorecard. First of all, this graphic includes those individual overwater forecasts from North Atlantic Basin TCs with dropsondes and DO2 and with H-dwarf cycled covariance. We have the that full sample that I just described, and then stratified down by intense initial classification into tropical storm, category 1 to 2 hurricane, and category 3 to 5 hurricane. That's the x-axis, the y-axis. You can see the little colored tabs. Those are the different sensitivity experiments on the bottom right as a reminder. And I'll also pop up the different experiments as a reminder when I get to a result that requires that. And this is just for Vmax. So what do we see here? What we see is overall mostly blues and dark blue colors. Again, the relative impact categories are on the bottom left. What the blues and dark blue means is that removing dropsondes anywhere leads to degradation. But let's look at this purple experiment here. This purple experiment is the no vortex experiment. It's that experiment I just popped up there. Dropsondes are not allowed within 250 kilometers. You're removing dropsondes from over the vortex, not allowing them to be assimilated. And there are 2 dark blue squares. And no vortex has these dark blue squares, which means that removing these in-vortex dropsondes actually are leading to large degradation relative to having them. Now, these in-vortex dropsondes actually contributed to a majority of the overall impacts of the dropsonde observing system for PMIN and also for size variables. So takeaway number 3, track forecasts of weak TCs benefited more from environmental sampling, and track forecasts of strong TCs benefited more from in-vortex sampling. Another relative impact scorecard, this one only looks at the tropical storm category 1 to 2 and category 3 to 5 impact. This is for track forecasts. I'm going to go through each of these individually. So let's look at the tropical storm column. In the tropical storm column, only one experiment was highlighted. That was a purple experiment. That's the experiment shown here. This is the experiment that did not allow dropsondes over the vortex. And what we see is that when we remove those in-vortex dropsondes, we get moderate improvement. And so that means that the synoptic environment dropsondes are very important or key. Let's look at the next column, category 1 to 2 hurricanes. Category 1 to 2 hurricanes, in that column, the only sensitivity experiment that was highlighted was the gold one. That was the one that allowed dropsondes over the vortex. In other words, removed those dropsondes in the synoptic environment. And this result suggests that removing synoptic environment dropsondes leads to moderate improvement for category 1 to 2 hurricanes. In other words, in-vortex dropsondes are key. In the last column for category 3 to 5 hurricanes, again, one experiment is highlighted. It's the blue experiment now. That blue experiment denied inner core dropsondes. And so this result is that removing inner core dropsondes leads to moderate degradation. In other words, suggesting that inner core dropsondes are key for category 3 to 5 hurricanes. So putting all of that together, this suggests that as intensity increases, the most important area to sample for track forecasts actually moves inward from the synoptic environment for tropical storms all the way to the inner core for category 3 to 5 hurricanes. Takeaway number 4, inner core only sampling strategy should be avoided, supporting a change made to the U.S. Air Force Reserve sampling strategy in 2018. So what you're seeing here is a typical C-130 alpha pattern. The track is in black, and you see two different colored dots on here. The cyan dots are the standard dropsondes through 2017. Then after 2017, there were additional dropsondes added at the endpoint of this pattern. If you look at just the blue dots before 2017, that kind of looks like one of our experiments. It kind of looks like our ICO experiment, where we only allow dropsondes within the inner 75 kilometers. Now, of course, in our experiments, we're not just keeping those dropsondes from the C-130. We have the P3 in there, G4s in there, but we can use this experiment, the ICO experiment, and compare it to a no-drop baseline to kind of give us a sense of what this change would have done, or if we were in a world where we still only had those inner core drops, what the results would be. And that's what you're seeing here now. These are individual forecasts from North Atlantic Basin TCs with dropsondes and DO2 and with H-wave cycled covariance, stratified down by initial classification into tropical storms, category 1 to 2 hurricanes, and category 3 to 5 hurricanes. So for tropical storms, we see there's some short-term degradation of intensity and size when you only have inner core drops. For category 1 to 2 hurricanes, from 60 hours onward, there's some degradation across the board. And then in particular for category 3 to 5 hurricanes, there is degradation of intensity from 60 hours across the board when you only have inner core drops. And so what these results suggested to us was it was actually better not to sample TCs at all than to only sample the inner core. So this is what led us to this takeaway that it was good that this sampling strategy changed in 2018 to include dropsondes outside of just the inner core. Okay, so let's summarize this section. So this project, again, marks the most comprehensive assessment of the relative impact of dropsondes on TC forecasts of track intensity and size to date. There were 4 main takeaways that I covered, and that's the ones that are shown here. But overall, results are suggesting that substantially increasing sampling with dropsondes in certain regions could further benefit forecasts. Now to sum up all 3 of these sections, what are the main takeaways here? So from the first section, again, MAE and MAE skill alone or together even can be misleading, even if you have a large sample size. So we really need to stop using them alone for verification. One solution, augment the MAE and MAE skill graphics with the consistency metric. It lends confidence to results found, but also maintains simplicity. Main takeaway 2 from the second section, overall dropsondes are extremely valuable for TC track intensity and size forecasts, but the performance is heavily dependent on DA quality. And from that last section that I just went over, overall substantially increasing sampling with dropsondes in certain regions, particularly that in-vortex region, could further benefit forecasts. Now, while these studies represent the most comprehensive assessments to date, a lot more needs to be done on both on the OBS modeling and DA side and also on the research side. So I'm going to talk about some improvements that can be done to the OBS modeling and DA side. Now, in our sample, which was a 4-year sample, only 30% of individual forecasts from North Atlantic Basin TC had dropsondes. Now, while assimilating dropsondes in every TC forecast would likely lead to even further forecast improvement, obviously that's really not feasible. So we have 3 recommendations. So the first, let's aim to increase the number of cycles with assimilated dropsondes. You could do this by having more dropsondes, but you do need increased funding. Again, they're expensive and expendable. Or with remotely sensor recon that already continuously samples the wind and thermal field that we know what we hope and know would likely improve TC forecasts. So we need a lot more work done on getting those additional data types into our models. And so I'm going to give you this general schematic of what a future could look like here, an ideal scenario on the top and what more likely will happen on the bottom. So the x-axis is your radius distance from the TC center. Everything in cyan here are the current release points for the dropsondes. I have annotations on the bottom. You have your center, RMW, your midpoint, your inner circ and endpoint, your outer circ, and then your targeting as well. In the top panel here, the ideal situation, we get more dropsondes. Obviously, it's not terribly feasible, but what would we do with them if we can have them? What we would do is we would more heavily sample around our suggested R34, our suggested R50, and around R64. We'd also sample a lot more in the in-vortex region based on the results of our paper that looked at the relative impact of dropsondes on TC forecasts. More likely, what we'll need to do is keep current dropsondes where they are, though that also might not occur. But increase this remote sensing capability, increase the assimilation of recon that we already have, and get work on that to make it optimized as possible to assimilate into models to hopefully improve our forecasts. So what else can we do? So we can improve observation processing and quality control. We can use Dropsonde data to its fullest capacity. For example, assimilate quality controlled full resolution data in both HWRF and then other models at NCEP like GFS. And ongoing work at AOML suggests that this should considerably benefit forecasts and analyses. And finally, another thing we could do is improve our DA methods by investing in superior methods like 4D NVAR with model cycled covariance, and also by tuning observation errors and error covariances for that we can improve the use of our already existing data that's assimilated. Now, making these changes should lead to TC forecast improvements. Again, nothing is guaranteed, but research that have been done has suggested that that's possible. But there are other large sample research efforts that are still needed to quantify the impact of current observing systems on TC forecasts. And so I'm just going to touch on one of those efforts that I'm personally involved in. I'm currently quantifying the overall and individual impact of 2 recent G4 flight track changes on TC forecasts. The impact of the G4 overall and these individual changes do need to be quantified, and ways to further optimize the strategy really needs to be assessed. So what can we do with that? We can deliver these optimizations as guidance to HOT and NHC for use during G4 flight track planning. So let's say that the G4 or a particular G4 pattern might be most impactful when flown in a tropical storm, and not as impactful when flown in a hurricane. This guidance delivered is going to indicate those different types of distinctions. And to do this, what I'm doing is I'm running halves for TCs with past G4 missions between 2020 and 2023. The experiments I'm running are shown here. We have our all-R experiment, which allows the assimilation of recon from all the planes, the C-130, the P-3s, and the G4. The G4 here is in green. Then I have an experiment that denies the G4 recon entirely. That's the no G4 experiment. Then the next experiment denies the recon from the G4 non-standard pattern, which is everything except the standard inner and outer circ. And then finally, I have the NOAA experiment, which denies G4 recon from just the inner circ pattern. And so if you'll be at AMS Tropical Conference, I will be talking about some of the results from this project. And so definitely check that out if you're there. And so I want to thank everyone for your attention. I know I covered a lot of different things in this talk. I'm putting my main takeaways up here, and I will take any questions, and I'll check the chat as well. So thank you so much.
Thank you, Sarah. Wonderful talk. It looks like we have a couple of questions on the chat. So I will start with the first one that came in, which was, in 2017, 2020, did the Dropsonde equipment change or remain consistent in the manufacturing and instrumentation? Would you happen to know that?
That is a good question. I don't recall. I think I saw some people on this call who would know that information. I will say that the some of the sampling strategies did change, like the addition of like the endpoint drops in the C-130. For an example, for the G4, there were some changes, like the addition of the inner circumnavigation, changes to the targeting methodology using some of the Rhine-Torn's ensemble sensitivity metrics at outer radii. But yeah, if someone on this call has that detail about the specific Dropsondes, and just to follow on that, the drops were from the P3s, C-130s, on the G4, and then there were, I think, maybe a couple of GH flights in here as well, just giving some more details, and all that is in the paper.
Thanks. There's another question here asking if you are using the NHC best track radii to verify the radii.
Yeah, so everything is, I know there are downsides to that, but yeah, so what I'm currently doing is I am verifying against the NHC best track radii for 34, 50, and 64 knot wind. One of the things I might be doing a little bit differently than other people might be is, instead of averaging around all the different quadrants, I'm grouping all of the quadrants in together. So that is potentially one different, but yes, that is the radii I'm verifying against.
Right, there's another question here on how risky is it to modify Dropsonde observing strategies without knowing how these changes would affect, say, ECMWF forecast? That is, are these results at all generalizable to other models used by NHC?
That's a really great question. One thing that I'll mention that I mentioned in the talk was one of our results with assimilating drops, that we found that the intensity dependent impact. I won't scroll back through the slides. It was consistent within HWRF and the basin scale HWRF in terms of the results found, in terms of the fact that hurricanes had more direct impact when the dropsondes assimilated. But when we had a study that looked at the GFS, we saw the opposite results. So I don't know if the results are generalizable to other modeling systems. More of these types of studies need to be done so that we can answer. I see James asked that. James, those questions. There's no, you can't really know how risky it necessarily is. What I can say is that in the Sippel et al. 2022 study, we looked at the impact of drops and HD OBS in the GFS V16 compared to before the additional drops in the HD OBS were added, and we did overall see some improvements. But again, that's not changing the strategy in terms of, oh, let's only fly in a tropical storm versus let's only fly and let's not fly in a hurricane. I think in terms of those optimizations, in particular for let me go backwards one slide, particularly for this project, a lot of this I feel has to do with also conserving of resources as well. Like in those particular situations, if let's say the dropsonde supply is running, well, this is all recon, but if the dropsonde supply is running low, and these types of decisions need to be made, let's say when it's approaching landfall, this is some really great guidance that can help with that. I'm sure other people have some interesting insight. They feel free to chime in, or you could reach out after and discuss that with me. But those are my thoughts on that.
Thank you. Looks like we have two hands. Richard, go ahead, and then Holger after that.
Hi, Sarah. It's Richard Pash here from the Hurricane Center. I know you recently reported on the impact of G4 SONS at the meeting, the TCORF meeting, and showing the scorecards for that. And the results were a lot more pessimistic than these. Yeah. And that was, I guess, in the context of halves. Yeah. Were you suggesting then that maybe it's the DA that's being used that needs to further improvements here to get those results to reconcile more with what you're showing here, which is obviously a lot more favorable?
Yeah, these results definitely do suggest that perhaps with a have cycled DA have cycled covariance, we might get better results than we saw. There was also one nuance that I was using HAVS A for that assessment, and Jason Sippel had performed some ad hoc experiments looking at the impact of recon compared to no recon in HAVS A, and the same thing in HAVS B. He saw that HAVS B performed a bit better there, particularly for weaker TCs. I do think that given these results, improvement to the DA system, we need more investment in those DA system in order to get these better results from our recon. I do think that's what's going on. I'm actually kicked off after that meeting, kicked off runs with HAVS B for that project. Again, just for everyone on the call, this is the project that we're chatting about. I did kick off runs with HAVS B, so hopefully I'll have enough maybe done by the tropical conference so that I could comment a little bit more on that. But that is what these results are suggesting.
All right, thank you. Yeah, I'm glad to hear that, because I was worried that we were wasting our time here tasking the G4. So yeah, this is a lot better.
Okay, let's have Holger come off mute.
Yeah, Sarah, thanks. That was a really nice talk. I really appreciate it. I can answer your question probably about the equipment change, and I have another question for you. Between 2017 and 20, I believe that was all the RD94. I think the change to the RD41 happened just after that. But I would be even surprised if that change would be detectable in any of the analysis you did there. I think that's small. But my question for you is, in assimilation, did you only assimilate the temp messages, i.e. the coarse resolution, or do the DA systems also assimilate high resolution buffer messages that have the location, especially in the inner core where it probably matters the most?
Yeah, so what gets assimilated are temp drop. It's not the full resolution profile, but there is drift that is included here when it's being assimilated. So if you have a TC near the a dropsonde near the eye wall of a TC, it's not being assimilated the whole profile down. There is drift calculation to calculate where it would be given the winds. I think that answered your question.
Yeah. Okay. Thanks.
No, there is work I'll follow up. There is work at AOML that's been done that shows that assimilating those more full profiles might lead to further forecast improvement. So that's area for future research that should be explored.
We have a question from Jason Sipple. Go ahead.
A comment, really, more than a question. So there are some similarities, though, between the basin scale work and the HAVS work. And a big one is that the basin scale work did show, fairly strong improvements at the longer lead times, right, for the impact of SONS, which is consistent with the HAVS, right? The HAVS work for the recon that I looked at, like for weaker storms, like there was some fairly substantial improvements at longer lead times. And in other work I've done with H4, right, where we took out all recon data. For weak storms, it was at the longer lead times. So there are patterns that emerge, but there are also differences, right? So I put in the comment that some of this, some of it probably has to do with different biases in different systems, but then there are also some things where there are some things in common. So that hopefully that leaves Richard with a little bit of a better taste.
No, I feel a lot better already.
All right. I don't see any other questions either. Oh, we've got one more hand. Last
Well,
question.
since we have a few minutes, I'll just pile on here. No, but I do think the other thing, and Jason alluded to this, but I'll say it more directly, is that I think this makes it really exciting to look at the multi-storm configuration in HAVS coming up, because we saw a lot of really great benefits at long distance based on the observations coming in, especially the SONS, and Sarah showed that in H4. So looking forward, it's going to be really interesting, especially as we sort of transition, hopefully, and Jason and I were just talking about this morning, maybe from a storm-centric type of DA to more of like a basin-wide analysis, right, and understanding these impacts. So I think this work really sets the foundation for some really exciting work that's ongoing in HAVS, in the next couple of years. So good work, Sarah.
Thanks.
Stan, you have your hand raised. Go ahead.
Yeah, I'll be real quick. Just kind of responding to Richard's comment. It's like, gosh, I wish this stuff was super consistent, and the consistency metric goes a long way to identifying it. But man, there's so much noise, and just like with the models and stuff. But I'm glad that this at least elucidates how in certain situations it can be helpful. But wish all this stuff was better. It was Dropsondes and the D4 were magical bullets to always improve forecasts. But I just thought I'd throw that in. That's what we all feel.
All right. Thank you again, everyone, for coming. And thank you again, Sarah, for giving a wonderful presentation. At this point, I will close the meeting. I'll stop recording. And everyone, have a good day.
Thanks, everyone.